I'm Stephen Edwards, and here I'm going to talk about sprite graphics, which is a particular technique for generating relatively robust graphics displays, typically for video games, that was invented 1970s, 1980s, when memory was very expensive. Let's start, as I always like to, with Pac Man. Now, this is an amazing game, and I imagine most of you have seen it, and it's pretty remarkable. What I want to do here is pause and take a look at the copyright date of 1980. Now, it's difficult to wrap your head around what computers might have been like in 1980, but to give you one reference point, Pac Man has an entire 4 kilobytes of memory. That is 496 bytes total. Now, there's a problem. The resolution, even though it is low, it is still 224 by 288. And that's that's over 64,000 pixels worth. Now, even if you use 1 bit per pixel, that still requires something like 8 kilobytes of memory. So the question is, how do you display something like this using only 4K? Now let's look carefully at what we have here. This is the demo mode. I'm going to put in some money, start the game, play a little song, and you'll notice the maze is static. Pac-Man moves around, the ghosts move around, we've got blinking lights, we've got scores and text. Let's freeze that and take a closer look. Let's look at the maze for a moment. You'll notice the walls are very straight. It's very regular. It's actually symmetric left to right. Doesn't need to be. All the walls are kind of the same width. There's maybe like 1 or 2 different choices. All of the dots are very evenly spaced. All of these should sort of give you a hint that, some kind of computery is going on. Let's put a grid over it and see what it looks like. With the grid, it's pretty obvious what's going on. This is an 8 by 8 pixel grid that I've overlaid, and now you can see that the text is on 8 pixel centers, all of the maze pieces are in 8 pixel centers, all of the dots are spaced by exactly 8 pixels, even the little Pac-Man down in the lower left are on 8 pixel centers. Let's look even closer. As we zoom in, it becomes really obvious what's going on. We have a variety of tiles, as they're called, and each tile is 8 pixels by 8 pixel. One such tile is the dot, 8 by 8. Another tile is horizontal maze piece. Another tile is rounded upper right corner of a maze piece, and so forth and so on. Even the big dot here you can see is exactly 8 by 8. So what's going on here is the background is described as an array of tiles. Each tile is 8 by 8. And by doing this and making most of the tiles the same, we save an enormous amount of memory. Here's another example of tile-based graphics. This is Tunnels of Doom, 1982. This is running on the Texas Instruments 99-4A computer, and we're actually going to talk about the chip that this uses. Anyway, take a look at this. You can very clearly see the effect of the tiles, right? The 2 O's are identical, the 2 N's are identical. Everything seems to be spaced on 8 pixel boundaries. And then you have silly things like the guy's head is very clearly an 8 by 8 pixel thing. Here is Super Mario Brothers. It too uses more or less the same system as Pac Man. But if you notice, it scrolls smoothly, very much unlike Pac-Man's maze. But if you look again, you'll find a very, very regular look to the background. So again, we've got 8 by 8 pixels. We've got text at the top that are very obviously 8 pixels wide. We have the absurdly regular ground here that happens to be on a 16 by 16 pixel pattern, and look at things like the bushes here, and I'm using the term in quotes, that are obviously made from multiple things duplicated. Now, the thing to notice here, like in Pac Man, we've got a bunch of things that don't work on 8-bit boundaries. And so here we have Super Mario. We've got the little bad guy here. What is that, a Koopa? This moves smoothly, and so the question is, how do you do that? The answer is sprites. Here's a chip. This is the TI TMS 9918 video display processor, released in 1979. It was at the heart of the TI 99-4A personal computer that most people have forgotten about by now, and was used in a number of other systems as well, notably the Colecovision. It embodies the notion of a sprite, which you can think of as being a tile that you can place at an arbitrary X and Y position on the screen. Now, what we have here is a figure showing a very awkwardly drawn car behind a tree with some clouds in the sky. And this diagram here, taken from the data sheet, shows how that image was put together. So the way it works is we have 8 individual sprites. Each one of them can be thought of as a small tile, and they are assembled one after the other as shown in the figure here, and then finally backed by a tiled background using the same technique as before. The idea here is that each sprite can be positioned at a precise XY coordinate. The drawback is you have a finite number of them. Here's a detail of how the 9918 generates the background tiles. In the TI documentation, they're called patterns. So starting from the left, we have the pattern name table. And what this does is for each 8x8 tile on the screen, it says which of 256 different tile images, which are held in the pattern generator table, it's in the middle here, is being displayed. Each of these patterns, each of these tiles is represented with 8 bytes, each bit of which represents a pixel. And each pixel in turn is one of 2 colors, therefore, because it's 1 bit. And the way that works is that this pattern color table at the bottom selects the 2 colors being used for that tile. Finally, on the right here, we have a diagram of what the screen looks like. There are 32 columns of 24 rows, and each pattern comes from the pattern name tables, looked up in the pattern generator table, and then displayed on the screen at its location. So here you can see how memory is being saved. The pattern name table is only 768 bytes long. The pattern generator table is larger, but in the case of Pac Man, say, the patterns themselves, the tiles themselves, are fixed and in ROM, and so don't count against the 4K that the Pac Man game actually uses. Here's the story for how the 9918 generates sprites. So as before, there is a table in memory known as the sprite attribute table that for each displayed sprite on the screen contains its X and Y coordinates, a name, which is an index into the sprite generator table that indicates the pixels that should be displayed for the sprite, and then a tag that controls its colors. Sprite generator table looks like a tile table, like the pattern generation table. It's just a series of bytes whose bits represent pixels, and eventually those groups of pixels are placed on the screen at the location given by the sprite attribute table. Now on the 9918, 32 sprites are supported, although you can't fit all of them on the same row at once. We'll get to that later. So the sprite attribute table has 32 of these entries in it. The sprite generator table has a variety of entries, more than 32 possibly, and this gives you the ability to animate the sprites by quickly switching the name. Say if you wanted a bird to fly, maybe you would have 2 images for that bird and quickly flip between them to make it look like the bird was flapping its wings. Here's the detail of sprite attribute table entry. It consists of 4 bytes. The first one is vertical position, and later it'll become obvious why you would want to put Y first in these little descriptors. Then the horizontal position. Both of these are in pixels. The third byte is the name, that is to say which image should be displayed for this sprite. And then the fourth one controls primarily the color. So there's a color code here that lets you select one of 16 palettes. And there's this funny thing, the early clock bit. The way that works is if it's set, it shifts the sprite 32 pixels to the left, which makes it so it can show up off screen to begin with. So you might want to think about this. Your horizontal position, if you want sprites to be able to come in from, say, the left side of the screen, maybe 0 should be to the left of the leftmost pixel on the screen. Let's talk about how you would build hardware that would display sprites and tiles like this. This image is of a group of 5 planes doing something known as digital skywriting, and you can see what's happening. Planes are flying from left to right on the screen and turning off smoke and turning it on at certain times to produce things like the O being displayed, and then the next character, we can't tell exactly what it's going to be, but it's got a vertical line in it. So imagine you're the pilot of one of these planes, and you need to be spitting out smoke at certain times. This is exactly what the hardware needs to do to produce a raster scan. It needs to be able to crank out the color of each pixel, not using smoke, but you get the idea, at exactly the right time. So think about what it would take to build something that would decide, okay, if I'm going to display an O, what do I need to know? Well, I need to know which plane I'm in. Am I in the top plane, the second plane, the third plane? That's the row of the video. Then I need to know where I am horizontally. Based on that, we should be able to figure out, oh, do I display smoke? Do I not display smoke? That's what the hardware needs to do. Here's another visualization of how this needs to work. This is a truck that's painting striped lines on a roadway. And if you can imagine what's going on, it's slowly driving forward. Then it has a paint sprayer that is turning on for a certain period of time, then turning off for a certain period of time, then turning on, and so forth. This is the same challenge that the graphics generator faces, where to put the sprites, how to draw the tiles, and it too is faced with doing a raster display. It only gets to decide the color of one pixel at a time, then it has to decide the color of the next pixel, and so forth. Let's look at what's actually going on inside the 9918. Let's work backwards through it. Starting in the lower right corner here is the video that actually is being generated. That comes through this box in the center that's marked color priority multiplexer and collision detect. So the output from this multiplexer is the color of the current pixel that gets fed through this color decoder and then out through the video logic. Now, if you notice, there are actually 5 inputs, each of these small black arrows going into it. Each of these contains one pixel coming from one of the 4 sprites that can be visible on a line, or the background, the pattern. And in the center here, we have color information about each of the sprites. If you remember for the 9918, the way the sprites work, there are 2 colors per sprite, sort of its foreground and background. One of them is often transparent. It is the job of this color priority multiplexer to sort all this out. If you have one of the sprites visible, if there are multiple sprites at that particular point, there's a priority. One of them goes in front of the other. If none of the sprites are visible, the pattern color is passed through to the video system. Now, let's look over here. These are 5 shift registers, 4 for the sprites and 1 for the current pattern. What these do is hold 8 pixels worth of data. And the way I think of them, this is like the smoke generator on the airplanes or the paint squirter on that truck. What this does is this holds 8 pixels ready to go, ready to be squirted out at the right time. Now, for the pattern, we're always spitting out the next pixel for the pattern, for the tiles in the background. For the 4 sprites that can be visible on a line, what these shift registers do is wait until it's their time to start squirting things out. This is just like the airplane deciding when to emit smoke. Once the sprite becomes visible, once you've gotten to the column where the sprite starts, you start squirting out pixels one after the other in these shift registers. Now, finally, in the lower left here, we have 4 sprite down counters. What these do is keep track of how many pixels there remain before we need to start spitting out the pixels for the sprites. What happens is that the x-coordinate of each sprite is loaded into these down counters, and they count down 1 per pixel. As soon as those down counters reach 0, as soon as one of them reaches 0, it starts the corresponding shift register to start pumping out the pixels. Now, the whole rest of this diagram is primarily registers for various control things. So there are things like a register that says where in memory the sprite attribute table begins, where in memory the name table, this is where the sprite pixels are actually stored. Similarly, there's a pattern-based register for the beginning of the pattern table. The other thing that's not shown in this data path diagram is all the control, deciding what gets loaded when and how. We'll talk about that in a bit. Here's another gaming console that used the sprites and tiles model. On the left is the Nintendo NES, which we had here in the US. On the right is the smaller but functionally equivalent Famicom, also made by Nintendo, distributed primarily in Japan. Came out in 1983. They ultimately sold over 60 million units of these things worldwide, which is just insane. It had a whopping 2 kilobytes of RAM built in, although typically what you do is you plug a cartridge in, and that would have a substantial amount of ROM. So for example, Super Mario Brothers had 40 kilobytes of ROM in it, which included all the graphic information. This is a step up over the 9918. It permits 64 sprites, and you could have a maximum of 8 of them per line. And the sprites were better, more colorful. They allowed 2 bits per pixel. The resolution was still pretty low to accommodate normal TVs, just 256 by 240 resolution. Here is the block diagram of the picture processing unit, or PPU, the custom chip that Nintendo put in the NES Famicom. This image comes from a patent, and the reference is at the end of this video. Overall, you can see it has a very similar layout as the TMS 9918 and looks like it was actually designed with the TI documentation in hand. I recommend you turn the tables on Nintendo and read their patent as you're designing your video generation logic. As with the 9918, we have a large video multiplexer that's selecting among the 8 visible sprites or the tiled background. And again, for each sprite, we have 8 pixel shift registers, attribute registers that hold color palette information, as well as information about whether the sprite is mirrored horizontally, and horizontal position counters that again count down from the left side of the screen to keep track of when the sprite becomes visible. In this diagram, we also have more details about the tile generator, which are these boxes on the right. One other interesting thing about the PPU here, Nintendo put the sprite attribute table on the PPU chip itself. We could see it in this box up here, listed as 64 words of 29 bits each. The data path we just looked at is only half the story, of course. What you can do is go and read the Nintendo patent. You can also find cases where people have reverse engineered the Nintendo PPU. Here is a summary of what it is doing operationally. The way this system works is on a per line basis. During the horizontal refresh time, this is when the electron beam is being dragged from the right back to the left side of the screen, the PPU is busy preparing to display the next line. So what it does, the controller inside it goes in, reads the color palette from memory, stores that within the PPU, begins to read the tiles, figures out where it's going to look for tiles, looks for the tile bitmaps, and scans through the sprite location information for all 64 possible sprites. For each of those sprites, it determines, is it on the current line that's being displayed? If it is, it takes this information from the sprite attribute table and loads it into the horizontal position counter, the attribute register, and the shift registers for the sprite pixels themselves. Once the line becomes visible, the PPU shifts over to primarily reading tile information, and then tile bitmaps, loading those into the appropriate shift registers. All of the sprites have been taken care of. All that happens during the line is that the horizontal counters are decremented, and when each horizontal counter becomes 0, it starts spitting out the pixels for that sprite at that point. The control for the PPU is relatively complicated, but if you think in terms of what information needs to be gathered to display a line of pixels, it becomes pretty obvious what it needs to do. Here's the memory map for the video memory used by the PPU in the Nintendo. It consists of 3 broad regions. The pattern tables are the actual bitmaps for the tiles and the sprites. The name tables are the tile numbers plus attributes about each tile, so for example, which color palette it uses. And then finally, the palettes are groups of 16 colors that are selected from roughly 60 that can ever be displayed on the screen. The Nintendo, like the 9918, uses a common trick known as color palettes. Rather than representing each pixel with 24 bits worth of color information, which is sort of the standard these days, they would represent individual pixels with 2 bits, 4 bits, 6 bits. And the idea would be that you would then use these bits to go and look up the actual color that you wanted from a palette, which in turn would eventually map out to, in the case of the Nintendo, one of 64 colors that could be displayed on the screen. And this is a very effective way to reduce memory usage. Here's the detail about the NES's sprite attribute table. Each sprite, 64 are supported in hardware, and again, you can only have 8 per line. Each attribute table entry is 32 bits, of which 3 aren't used. This is where they get the 29-bit number that showed up in the patent. First byte is the Y coordinate. You use this to determine whether the sprite is visible on your current line. The tile number, tiles and sprites use the same group of bitmaps. And each such tile, each such bitmap actually consists of 16 bytes. The first 8 are the least significant bits for the color. The next 8 are the most significant bits of color. So you have 2 bits per pixel here. The third byte in the sprite attribute table allows you to horizontally and vertically flip each sprite individually, depending on bits. There's some sort of priority control bit, then 2 additional color bits. Finally, you have the X coordinate, 0 to 256. Here are some references on sprites and tiles. Collins's article is a nice summary of a bunch of techniques, including the sprites and tile technique that was used throughout the so-called 8-bit computer graphics area. This is the 1980s that we've been talking about. All the rest are related to the Nintendo Entertainment System, which is now very well documented. People have reverse engineered it and found internal Nintendo documentation to the point where people are still actively writing games for this. At the bottom here is the patent from which I took a number of the images in this presentation.